Mm. Yeah, so today I want to tell several things about, for example, about degenerate fields. So the first thing is fusion rules for degenerate fields, and what are the other examples of degenerate fields? So we already know that if we take phi 1 2 or phi 2 1 and uh, uh, act with this on some state alpha, then we will have with some coefficients alpha plus b over 2 plus b over 2 plus with some other coefficient alpha minus b over 2. Or in other words, we can say that conformal blocks with a degenerate field, so it is called either by wavy line or by dashed line. The space of such conformal blocks with phi to 1 dimension of the space equals to 2. And representatives of conformal blocks are those with no, not of this one, but of this one. But, uh, but now ask the following question: what happens if we add two degenerate fields? So if we add and by the way, this rule can be written like this: that phi to 1 tensor alpha is alpha plus b over 2 plus alpha minus b over 2. This is a way to write this fusion rules. So it's not the usual tensor product of representations of the Versor algebra, but it's some operation of this kind. Actually, if you want to write this tensor product explicitly, we can do this. We should care about the central charge, because if we just take just usual tensor product, the central charge multiplies, adds here and here, but we can write some clever definition which comes from this contour integral. But anyway, this can be depicted. This can be written like this. And now let us ask what happens. Consider this object. So the question is, what is the dimension of the space of such conformal blocks? So it is both phi to 1. What do you think? No, why? When we perform this first fusion, we can add either add plus b over 2 or subtract b over 2. When we do second fusion, we also have two choices, whether to add b over 2 or subtract b over 2. No, what do you mean by degenerate? No, first here we have some alpha. Here we have uh, uh, alpha plus epsilon b over 2. Here we have alpha plus epsilon b over 2, original plus epsilon prime b over 2. So dimension is 4. But now let us think about this in some different way. So we know that conformal blocks can be written in different ways. Like we can first fuse these two fields and then add two more fields by fusing it here. But we can first collide these two degenerate fields and then consider fusion of what appears after this. So let us say that a space of such conformal blocks is actually isomorphic to a space of such conformal blocks. So in here we obtain something. So now let us see what happens if we consider the fusion of two degenerate fields. So let us consider phi to 1 tensor phi to 1. So phi to 1 itself is some state with charge minus b over 2. So it is minus b over 2 minus b over 2 plus minus b over 2 plus b over 2. So it is 0. So it means that a fusion of phi to 1 with phi to 1 gives some field phi 3 1 plus plus 0. And so we see that this space is a direct sum of two spaces. One is where we have 0 in this channel, and 0 corresponds to identity operator. To identity operator and all of its descendants, plus some space where this field here is 531. And we know what are possible restrictions on this charge. So we see that there are two situations when it just equals to alpha. So it is alpha. alpha. So in this case, when it is 0, then there is only one conformal block with charge alpha here. 0 alpha. But if it is F31, so if you have this degenerate field, it means that now there are three possible options, and so it is spanned by conformal blocks with uh, 5, 3, 1, and here alpha plus b alpha. Just alpha as before, and in the same conformal block with alpha minus b. So we see that fusion of two degenerate fields generates a fusion of two ones generates some other field phi 1, and we already know about this field that it has fusion rules similar to those of phi 1, but with three possible shifts. So looking at this picture, we conclude that the fusion rule of phi 1 was alpha is alpha plus b plus alpha plus alpha minus b. Right? And of course, fusion rules for 0 just itself. So, oh, is it fine? So, and now, principle we can say and so on, and if we now try to consider some field phi n1, then phi n1 with some alpha, I will give sum from what? From n minus 1 over 2 to from 1 minus n over 2 to n minus 1 over 2 k equal alpha plus kb. We can also ask what happens if we compute a fusion of phi of phi n1 with maybe better to start from 5 to 1 times 5 and 2. So if it now I can consider 5 to 1 times 5 and 2. It corresponds to what? It corresponds to a study of conformal blocks with so here is 5 to 1 and here is 5 1 2. So here possible value is alpha. Here it's alpha plus epsilon b over 2, and here is alpha plus epsilon b over 2 plus epsilon prime b inverse over 2. So there's some random values of alpha, in the sense that there are no relations between them, and so we can say that span of such conformal blocks is the same as the span of such conformal blocks. With field 5 to 2 here, and with such shifts here. So here we get just a field 5 to 2. And then fusion of this 5 to 2 with alpha. So the consequence of all this is the following: that this the structure of this fusion, I don't know if you can call this category, monoidal category or whatever. So the structure of this fusion product is precisely the same as the structure of SO2 representations, SO2 times SO2 representations. So so fusions of degenerate fields the same as tensor multiplication of SO2 times SO2 plus SO2 plus SO2 representations. So this 5 to 1. So phi and m corresponds to corresponds to a, a, n-dimensional representation times m-dimensional. Maybe better to write to like, oh, so it's like n-dimensional for the first SO2 algebra and m-dimensional for the second SO2. So, for example, phi1 corresponds to a fundamental comma trivial, and phi12 corresponds to a trivial comma fundamental. So, and in particular, if we consider multiplication of phi n m and phi n prime m prime, it will be equal to sum of let me think. Probably from absolute value n minus n prime plus 1 probably. To n plus n prime minus 1. And the same for m. So n 2 primes equals to m 2 primes equals to so this is phi and 2 primes m 2 primes. So, and the point is that it and also so it's for degenerate fields, and if we ask about generic field, then a generic field corresponds to Varma module of this SO2. And this multiplication law corresponds to multiplication of Varma module by this representation. So we get a highest vector for any vector of this finite dimensional representation. And so the point is that all this can be obtained just from associativity of fusion and from the fusion rule for degenerate field phi1 itself. So is it clear? I'm saying that if we multiply phi to ones, and so if you see that fusion of phi to one corresponds with a multiplication of gamma module by fundamental representation, and uh, that a fusion of phi to one also generates some three-dimensional representation plus one-dimensional. Then it is enough to say that all this I don't know, category or what is the same as that for representations of SO2, because we can generate any fundamental representation of SO2 just by tensoring. Also, we can generate any finite dimensional representation of SO2 by tensoring fundamental ones. And so I can construct this recursively, and so I identify this representations which were obtained initially, and see the fusion rows of new fields. In a sense, we can consider just nth powers of phi to one, and then say that okay, here we see phi 3 1. We already know it's fusion rows. We see phi 5 1. We also know it's fusion rows. And by the way, the sum should be. I don't know how to write this, but it is a sum with step 2, step equal to 2. So let us write like this, and okay, we obtained phi 3 1 and phi 1 y 1, phi 1 1, which is 0. So is it okay? So and by the way, there is a possibility to consider a theory which contains to consider such a theory that some of these degenerate fields will be identified, and that they have the same dimension. So it is what is called minimal models. In this case, we should say that B equals to I square root of P over Q. Then central charge will equal to 1 minus 6 P minus Q squared over PQ. And if you look at the dimensions of these fields, then delta NM is equal to so it is it is 1 minus n over 2b plus 1 minus m over 2b times b inverse n minus 1 over 2b plus m minus 1 over 2 b inverse. So it is b plus b inverse. No. Sorry, it is 1 plus n. So if you substitute this, then we get p minus q squared over 4 pq plus and p minus mq squared over 4 pq. And so what can we notice here? That if so the first observation is that if we shift delta, if we shift n plus q and m plus p, then this dimension is just the same. There should be also another transformation. Let me remember this. So another transformation is just a shift of one of these variables by q, like delta of n plus q m equals to what we had originally, minus q squared over 4 for PQ plus P minus MQ plus plus Q over 4 PQ. Oh, maybe plus 2Q. Yeah, I'm not actually sure. So it will be n plus 2Q M plus NP minus NQ plus 1. There is also such symmetry, and actually it turns out that we can restrict the space of fields in yes, thank you. So the space of fields in this theory can be restricted by this rectangle from so this is 5, 1, 1. So so 2 PQ, if I remember correctly. Or P minus 1, P minus 1. Or maybe no, it's P minus 1, P minus 1. And also, actually, there is also such a refraction symmetry which restricts it to only one half of this rectangle. No, maybe. So it depends on parity. So it's either just division by 2 or something a little bit more complicated, but in general we have one half of such field, and also Another comment is that if we want unitary series, then P should equal to Q plus 1. In this case, the central charge equals to 1 minus 6 over P plus 1. So if so minimum models are constructed only from this degenerate fields. So, and of course we should also add complex conjugates to them, but in general it is like this. And by the way, concerning this degenerate fields, so there should be some reason for this fusion rules for the field phi nm. It should be clear why. There is some equation of order nm satisfied by a three-point correlator, and since we know that it is of order nm, it means that it involved some L minus 1 to power nm, which means that this delta nm had no vector on the level nm, right? So like for phi to 1, it was no vector on a level 2. Because Uh, but if you go to the case of minimal models, we see that since there is this symmetry for n and m, like this delta can be represented in different ways. It means that the same Fermat module can be represented in this way or in that way, and so characteristic property of the minimal model is that in that Fermat modules of its degenerate fields have at least two null vectors. So in general situation, there is such kind of picture. General C. And for minimal model, there isn't this picture. And even more, these modules start to intersect, and these submodules can start to intersect in the sense that some vector can be descendant of both of these null vectors. So like this, also some new vectors on higher levels, and it leads to the fact that if we want to write a character of minimal model in terms of Versoix character, then we should first subtract naively these two submodules, then realize that we subtracted too much and add another Verma module, and so on, and usually there is some infinite series. Not usually, but always some infinite series for the ratio of this character of minimal model by the Versoix character. So, actually, I don't want to tell much about minimal models apart from the fact that they exist, and they correspond to. So these unitary minimal models correspond to a fixed point of a normalization flow of for field theory, like d mu phi squared plus v of phi. So these different p's correspond to different powers of potential. And, it, it's also possible to understand because there are equations of motion satisfied by field phi 2, which are identified with equations of motion in a quantum version of equations of motion in this field theory. So there's some speculation of this kind. But are there any questions about this? So then probably I would like to tell about the origin of this parameterization. Like C equals to 1 plus 6q squared. So so it's called Feigin-Fuchs angular momentum tensor. So it equals to 1/2 of g of z squared plus maybe, so let me try to write this correctly. Maybe plus I plus square root of 2 probably q d j of that. So we try to consider such a modified energy momentum tensor And first we need to check that it is actually energy momentum tensor. Uh, so, yeah, like this. Actually, maybe correct formula is this one. Yeah. So let us compute OP of T of Z with T of W. So it equals to uh, um, 1/4 of 1 over Z minus W fourth plus 2 over this plus so it was OP of this term with itself, and now the OP of this term with this one. So it's 1 over Z minus W squared. Mm, mm, oh. So is it fine? Yeah, I took OP of J of Z squared with dj of W. So now let us collect this term with central charge. So when we take uh, the first derivative, then we get no, let me write this. This is 1/2 Z minus W water. Hmm. No, so here there should actually be I over square root of 2. Yes, here's 1/2. So when we differentiate this, we get two factors, 2 and 3. And now about signs. When we differentiate in uh, z, we can say that that the, that it's negative power, so overall sign is -1. When we differentiate with w, here's still negative power, but it is minus w, so it gives sign plus. So we have two minuses here, and finally it gives 3q squared over z minus w quarter. So, and here here we have mm, 2.5 g of z g of w z minus w squared plus dz dw half g of so it is g of w squared z minus w. So here we have something like this. So uh, uh, the term at the second order pole is, of course, derivative of j, and a term and at first order pole is 1/2 derivative of j. So we can now take all these terms together. So this, 2 times this term is precisely what we want, plus iq or square root of 2 dj w or z minus w squared. And this term, the second derivative, is also what we want. It is All right. So it is actually the OP for the energy momentum tensor with the central charge. Okay. So, and uh, Uh, so, uh, of course, you can construct such an enrollment from tensor, but then you can ask, who are the primary fields for such an enrollment from tensor? So, is, for example, our original field J primary or not? So, sorry, let me check if recording this. So, if you compute OP with T of Z with J of W, then what what we get? The first term gives 1 over Z minus W squared and J of J of W plus dj of W or Z minus W. So for now it looks fine, but let us look at the OP of the last term. It gives plus I IQ over square root of 2 dz 1 over z minus W squared. So it is uh, so it means that if we try to perform a conformal transformation, so delta epsilon of g of w, which is equal to the integral of dz epsilon of z t of z g of w. It will contain the usual terms like delta epsilon prime of that j of w plus epsilon d j of w plus compute this one. So it's a bit similar to a transformation law of the energy momentum tensor. In that case, we obtained a third derivative, derivative of epsilon, and here it's second derivative. So if you compute analogous transformation for the field phi, then we will get so delta epsilon of phi will be then, so this, phi is j is I d phi, so it will be epsilon d phi plus minus q over 2 square root of 2 epsilon prime w. And and what is the meaning of this? We'll come to this later, but let us ask what is the meaning of this transformation property if we think about classical fields only. So if it is some classical transformation property, then it means that exponential of phi of maybe let us write some exponential of square root of 2 alpha phi. It transforms as so if it was phi of w, then it transforms to e to the square root of 2 alpha phi of w plus epsilon times 1 minus q over 2 epsilon prime, which is nothing but the q alpha, which is nothing but transformation property of no, how to say it? It's nothing like the contribution from Jacobian. So we can write it as e to square root of 2 alpha phi of w plus epsilon times d of w plus epsilon over dw to power minus q alpha over 2. So it means that such No, elongation of the energy momentum tensor corresponds to classical modification of the transformation law for the field phi. Um, and that changes transformation law for the exponentials, and it gives them some classical dimension. So now the transform fields with dimension. Well, actually, I don't like this Q alpha over 2. Uh, I'm not sure if it is correct or not. Uh, uh, so let me think. Ah, uh, of course it is wrong because uh, I missed the factor of 2 when differentiated by 1 over z minus w squared. So it should be 2 here, and it cancels this 2, and it cancels this 2, and it is just q alpha. And about and concerning the sign, uh, so actually, I don't like it because in principle I expected that it should be q times alpha, but maybe let us let us compute something and then check if the sign of q is this one or the opposite one. It's not so important. Oh, so what we checked already that this field J is not primary anymore, but we can expect that these exponentials are still primary because we knew that they were primary. So for q equals to 0, they were primary at the quantum level with dimension. So in this case, it should be minus alpha squared if you normalize it this way. Mm. And mm, so, mm, well, actually, or maybe after all, it means that I should change all minus size to all i's to minus i's in this computation. Sorry. So and so minus q. It's minus. It's plus. It's plus. Here it's plus. So then this expression like dw to q alpha times e to square root of 2 alpha phi is invariant. Yes, I'm saying that if this field had correct quantum dimension, and if we just added some classical correction to this dimension, then it is natural to expect that it is primary. It is still primary. And now, how to check this? It is easier to check it in the operator formalism. Namely, we can say that our field is placed at 0. So, and then computational DLP with this energy moment of this energy momentum tensor with primary field is just computational direction of the energy momentum tensor on a vacuum state. So let us remember our convention. So this current J of z is given by sum of an over zn plus 1 for integer n's. And we have chosen this normalization such that a0 acting on the state given by the exponential e to I alpha phi, it gave us alpha. So in that case, this normalization was more convenient. But and now it is more convenient to use this normalization with square root instead of I. So so if you have such convention that means that a0 acting on e to square root of 2 alpha phi, it gives minus I square root of 2 alpha e to square root of 2 alpha phi. And now let us write some formulas for ln's. Just take this normal ordering. So we get that L n equals to 1/2 of sum k plus m equals to n ak am normally ordered. It is from the first term. And on the second term, we need to take a derivative of g, derivative of j, and it gives what? It gives minus n plus 1 times an divided by zn plus 1. So together with this, it gives I q n plus 1 over square root of 2 an. So it is easy to see that if we take a positive L, it will contain so each term contains at least one positive A. So we conclude from here that L n greater than 1 acting on e to square root of 2 alpha phi is 0. Now the only question is what is the action of L0? L0 on this e to the square root of 2 alpha phi is what? It is 1/2 of A0 squared plus iq over square root of 2 A0 acting here. And now let us use this convention. So this term gives us precisely alpha q, and this term gives minus alpha squared. So and this is the dimension that we wanted alpha times q minus alpha, right? So and now there is a question: how to compute correlators how to compute correlators in a theory with such energy momentum tensor? So. So, for example, we want to compute two-point correlator of two fields of dimension delta of alpha, phi delta of alpha, of z, phi delta of alpha of w should equal to 1 over z minus w to 2 alpha q minus alpha, right? So no, I'm saying that we should have so this two-point function should behave like this. And now the question is, what are the correct fields to put here? So if you want to compute this correlator in this theory, because some naive idea is to take phi of phi alpha of z phi alpha of w phi minus alpha of w For example, like this. Uh, uh, well, it will give first of all it will look like these correlators have different dimensions, but they still give but their correlator is still non-zero, so it is something strange. So it also looks like mm, so it does not equal to this one. Mm. Mm. Uh, and it is clear from this formula that correct prescription for this correlator is uh, e to the square root of 2 alpha phi of z times e to square root of 2 q minus alpha phi of w. But that's not all, because if you write only this, then we will break conservation law of charge, and it means that we should add another exponential at infinity. It is e to minus square root of 2 q phi of infinity. And if you compute this correlator, so it does not affect the value of the correlator. It only changes the it only changes and this how to call it vanishing of so this conservation law for alphas. So the sum of alphas now should be equal not 0 but q, and it is compensated by this phi at infinity. So yes, of course. So I will tell. So later I will tell about Liouville theory, and in that case, it will really correspond to a coupling of curvature to this scalar field, and this corresponds to flat metric with singularity at a infinity. And so if you compute this, we see actually this formula. So it is 1 over z minus w to alpha q minus alpha. And so if you think technically about this field at infinity, so what is written here means that a state that is that it is a conjugate to state alpha is something like q minus alpha. So and if we try to think about this technically, then where this transformation property for J, so it's here. So if we perform a transformation W to W inverse, then this field is not primary under this transformation, and it will receive some correction which contributes precisely to no, so to which coefficient so we should multiply it by W, and we'll look at the constant term probably. I'm trying to say that if we perform inversion in this formula, then coefficients of a new current will be not just ANs, but A0 will be shifted by some Q, which comes from this term. And this is why we have this shift. Why we should have a field like this at infinity. So yes, so later I will tell about Liouville, but at the moment I want to say that such a fair-field representation allows us to compute some conformal blocks. For now, we know explicit formulas for which conformal blocks. So one example is non-conformal blocks. So the most recent example was this conformal block with the degenerate field. Now for 1, alpha infinity, alpha 0. So it equals to some hypergeometric function, right? But there was actually another example of conformal blocks for absolutely non-degenerate fields. And who can tell what in this other example? Okay. In which case it is possible to write some explicit formula for a conformal block. Well, first, some 4-point conformal block, I mean. What? So which dimensions which I just can I put to get, like, for example, for c equals to 1? I just want to say that if we consider free boson and consider correlator of this free boson, just correlator of the exponentials, it will be some conformal block with some specific charges, like alpha 0, alpha t, and here we should necessarily have alpha 0 plus alpha t. Because of this Yuan conservation law, right? Here we should have, so here it is alpha 1, so this state should be minus alpha 0 minus alpha t minus alpha 1. So uh, and what is the formula for such a conformal block? So it is a product of zi minus zj to power alpha I alpha j. So, well, it depends on convention. So it is for the exponential convention. For our convention, it will be a product of product zi minus j to minus 2 alpha I alpha j. So so it is what t minus 0 to power product of this. So it is t to minus 2 alpha 0 alpha t times another term is 1 minus t to this power minus 2 alpha 1 alpha t, and some 1 to some power, which is not interesting, and something related to infinity, which which is also not interesting, because like after taking the correct limit, it should disappear. So this is just such a simple expression for this conformal block, and oh, so to have this, we should have two extra conditions on the external and the intermediate dimensions. So we should have two conservation laws at these points, this one and this one, right? So instead of 5 parameters, we have only 3 independent parameters: alpha 0, alpha t, alpha 1. But and this was for c equals to 1. But no one told us that these exponentials are that we should consider only such energy momentum tensor with q equals to 0. We can say that we compute absolutely the same correlator, but energy momentum tensor is no different, and it would mean that so. For so this expression will be the same. Only a formula for dimension of this field at a infinity will change, and formula for other dimensions will change. But this principle is the same. We have some conformal block which has this explicit expression. But now the question is how to construct more conformal blocks. And the idea is the following. Uh, we can introduce so-called screenings. So what it means? We should take some field of dimension 1. Uh, uh, so and so if you have such field, so it means that it makes sense to consider such an expression phi of z dz, which is one form. So and it is invariant under the conformal transformations. Uh, but let us look at the following expression. So we can consider expression of t of z with phi of w. So it is what? It is phi of w over z minus w plus d z minus w squared plus d phi w over z minus w. So it is fine. It is some trivial statement, but less trivial observation in that what happens if you expand this LP around around the first point, around Z, not around W. So this is to see that in this way we get phi of z over z minus w squared. So if you now try to consider the following object. So let us now compute the commutator of the integral phi of w dw over some closed contour C, which we will define later, with t of z. So we know that commutators are always expressed as a contour integral around the second point. So it can be written as the integral around z dw, maybe, or it's fine, dw phi of z over z minus w squared. So, and it is a bit funny because you see there's a second order pole at this pole, but there is no first order pole. And this function depends on z and not on w. So we have just 1 over z minus w squared integrated in w around z, so it is just 0. So we see that um, if you find some closed contour to integrate this field of dimension 1, then it commutes with Virasoro generators. So if you now takes such operators in a free theory, then we can construct some other conformal blocks by inserting such operators. So and since such integrals are kind of transparent for the Virasoro generators, then this defining condition for conformal block will not be violated. So we can take everything and add as many scannings as we want. So, and who are the scannings? So this condition that dimension that the dimensions should be 1 tells us that like in delta of alpha is acute is alpha times b plus b inverse minus alpha. And if we ask it to be 1, then it follows that alpha should be either b or b inverse. So if you now have such, see, so probably we'll finish soon. Maybe just actually almost time to finish, but now we can say that we can consider not only a correlator of several exponentials, like we can consider not only e to root of 2 alpha 0 phi of 0, e to the square root of 2 alpha t phi of t, to the square root of 2 alpha 1 phi of 1, and something at infinity. But we can also add some number of the scannings. And in principle, we can also add this opposite scannings with B inverse. From one side, we know that it is a conformable block. From the other side, this integral can be computed explicitly. Mm. No, not computed and not necessarily computed, but at least it can be written explicitly. So it is called Coulomb gas representation. So, next time I want to tell a little bit more about this and to show that in some cases it is actually also a hypergeometric function, surprisingly. And I don't know if it is general phenomenon or it works only for c equals to 1, but such conformal blocks, such conformal block with a degenerate field can be mapped by some absolute non-obvious symmetry to such kind of conformal block, which does not have any degenerate fields, but has slightly violated conservation laws. So by GT correspondence, this transformation is the following. So there are transformations which permute. So GT correspondence tells that to construct mapping between dimensions masses in gauge theory, we should divide these masses like 2 plus 2 and construct one pair of dimensions from one pair of masses, another pair of dimensions from another pair of masses. And there are obvious symmetries, like we can permute these masses or these masses, and it does something with dimensions. But there is also a symmetry when we exchange two masses from different pairs, and it acts quite non-trivially on dimensions of conformal block. In particular, it maps conformal block with the degenerate field to conformal block with one scaling. So for c equals to 1. So so, so in some sense, these phenomena are related. It's maybe for that's all. Next time I'm going to tell a little bit more about the scanners and also about Liouville and about maybe next time or next week about classical limit of Liouville and of conformal blocks. Mm-hmm. Uh, it's explicit computation. So so this OP is fine, right? So yes, yeah. So it was important that dimension is 1. Mm-hmm. So if you have a field of dimension 2, then you can write a similar kind of formula, but like with t of z plus t of w. But in that case, residue is still there. But for field of dimension 1, it turns out that there is nothing. And I think that kind of explanation of this is the following. If you have some field which transforms like one form, then integral of this one form over some closed cycle should be invariant on the conformal transformations, because conformal transformations only move this cycle a little bit. So, so if it is closed, if it ends at some zeros of some function, then it should not be changed by conformal transformations. So, mm, okay. So are there any other questions? Mm, Okay. Well, thanks for your attention.